Hello, I'm Amashni. In this lesson, we will recap on everything that we have learned about triangles in these 9 lessons in the series. Can you remember that we first named triangles according to the lengths of their sides? We then further defined them according to the sizes of their angles. This helped us to divide triangles into 7 types. This tree diagram should remind you of what these are. We discovered that we could get right-angled, acute-angled, and obtuse-angled scalene triangles. We also get right-angled, acute-angled, and obtuse-angled isosceles triangles, but equilateral triangles can only be acute. We investigated the scalene, isosceles, and equilateral triangles in lessons 2, 3, and 4, and we found that each of them had special properties. We constructed our own model of the equilateral triangle and found that in an equilateral triangle, 3 sides are equal to each other. All the angles are each 60 degrees, and equilateral triangles have 3 lines of symmetry. We also constructed a model of the isosceles triangle and found that in an isosceles triangle, 2 of the sides are equal to each other. Isosceles triangles have 1 line of symmetry and that angles opposite the equal sides are equal to each other, no matter how long we make the equal sides. We then measured some cutouts and found that we can get isosceles right-angled triangles, isosceles acute-angled triangles, and isosceles obtuse-angled triangles. When we investigated scalene triangles, we found that none of the sides are equal to each other, and scalene triangles do not have any lines of symmetry. We also get acute-angled, obtuse-angled, and right-angled scalene triangles. While we investigated all these triangles, we discovered that we could draw special lines in each of these triangles. Can you remember what these lines are? We learned that we can construct the following lines in a scalene triangle. Angle bisector, the line that bisects an angle of a triangle. Perpendicular bisector, the line that bisects a line segment at a 90-degree angle. Median, a line from the vertex of a triangle to the midpoint of the opposite side. Altitude, a line segment from the vertex of a triangle perpendicular to the opposite side or the line containing the opposite side. As we constructed these lines, we found that they were concurrent. Here are 3 diagrams to remind you of how we defined concurrency. In mathematics, we say that if 2 or more line segments, rays, or even planes intersect at a single point, they are concurrent. The point at which they intersect we call the point of concurrency. In diagram A and B, the lines are not concurrent, but in diagram C, they are. In lesson 5, we investigated the points of concurrency of medians, perpendicular bisectors, angle bisectors, and altitudes. Do you remember that these points of concurrency each had a special name? The point of concurrency of medians is called a centroid. This is the center of gravity in a triangle. The point of concurrency of angle bisectors is called the incenter. The point of concurrency of perpendicular bisectors is called the circumcenter. The incenter and circumcenter both show a special relationship between triangles and circles. The point of concurrency of altitudes is called the orthocenter. In Lesson 6, we learnt about two theorems. To understand and remember these theorems, we translated a triangular grid pattern. By using this diagram, we saw that the sum of the interior angles of a triangle is 180 degrees. And we found that the exterior angle of a triangle is equal to the sum of the opposite interior angles of a triangle. We used the same diagram in Lesson 7 to discover a relationship between triangles and parallel lines. We found a pattern that reminded us of the teeth of a saw and learnt that this pattern helps us to see that the alternate angles formed by parallel lines are equal. We also found a pattern that reminded us of the steps of a ladder. This pattern helps us to see that the corresponding angles formed by parallel lines are equal, and that the co-interior angles of parallel lines add up to 180 degrees. In Lesson 8 and 9, we found that triangles could be called similar. Similar triangles are triangles that have the same shape but not necessarily the same size. We discovered 3 rules for similarity of triangles. Can you still remember what these are? The first rule is called the AA rule of similarity. It states that if 2 angles in one triangle are equal to 2 angles in another triangle, the triangles are similar. The second rule is called the SSS rule of similarity. It states that if 3 sides of one triangle are proportional to 3 sides of another triangle, then these 2 triangles are similar. The third rule we discovered is called the SAS rule of similarity. It states that if 2 sides of one triangle are proportional to 2 sides of another triangle and the included angles of the triangles are equal, then the triangles are similar. At the end of Lesson 9, we used our rules of similarity of triangles to calculate the height of a lamppost without having to physically measure it. We called this type of problem an indirect measurement problem. Thank you for joining me in this series of lessons. I trust that you now have a better understanding about triangles, their properties, and the theorems we associate with them. I hope to see you again soon. Goodbye. Bye.